I'm going to derive the moment of inertia of a non-uniform cylinder. What if the volume mass density of the cylinder changes as some function of the radius? So if the cylinder maybe is made out of a material, a dense material inside, and maybe it gets less dense as you go out. Or maybe it's made of very little density material inside, and then as you go out, it gets more dense, right? So it can have some kind of function, volume mass density as a function of R, can be some number kappa, which is some constant, times R. It could be R squared, it could be R cubed, R to the fourth, R to the fifth, or it could be some other kind of general function, R squared plus R cubed, okay? It could be anything. So in this kind of a case, it would mean the density is increasing as a function of R. So how would we find its IZZ? Okay? All we need to know is to find IZZ. Once we find IZZ, IXX is going to equal ML squared over 12 plus half of IZZ. We don't have to reintegrate for this. Whatever we get for IZZ, we put it here, take half of it, and add it to ML squared over 12, right? So the only thing we need is this one. So what we have to do is set it up like we did with a uniform cylinder. Do integral R squared dm, integral R squared rho dv, except that this time the rho you put the function in. So let's just do the original one, kappa of R, linearly increasing function of R. What would happen? You put that in here. dv is 2 pi r dr. For this one, I'm going to use just a simple one integral version, a cylindrical shell. So then you have IZZ is equal to 2 pi kappa. Then, of course, I need the L. And then you have here r to the what? Third, fourth, r to the fourth dr from 0 to r. And then you have 2 pi kappa L r to the fifth over 5. Now for this kind of a problem, you have the kappa remaining, some constant kappa. So what we have to do is we have to do another integral, and the other integral is this one. dm is equal to, m is equal to integral dm, that's how you start the integral. And then dm is equal to rho dv, okay? So what we need is a relationship between the total mass of the cylinder and the kappa. What does kappa need to be, and what is its relationship with respect to the mass, so that the total mass works out correctly, right? So we have m, rho is kappa r, dv is 2 pi r dr L. So this integral is very similar to this integral, except what? It doesn't have the r squared in front of it, right? It just has dm, not r squared dm. So it's going to be a very similarly looking integral. 2 pi kappa L integral r squared dr 0 to r. And its final result is m is 2 pi kappa L r cubed over 3. Okay, notice what? You see here, the 2 pi kappa L, the 2 pi kappa L. Here's what I can do. I can say 2 pi kappa L is equal to 3m over r cubed. 3 times m over r cubed. I can substitute that into this equation, and therefore I have an expression for the moment of inertia solely in terms of the mass. So I have here 3m over r cubed times r to the 5 over 5. What's the final answer? 3m over 5 r squared. Okay? Compare that to the moment of inertia of a uniform solid cylinder. The uniform, it was half mr squared. This one is 3/5 mr squared. So the moment of inertia of this cylinder is going to be bigger because the ratio of 3 to 5 is 0.6. The ratio of that is a half. So if you raise the two, which one wins? If you raise the two, the smaller moment of inertia wins because it's easier to rotate, you see? So why was this harder to rotate? Because the density of the material increased as the function of R, right? Now what if I had done kappa R squared? What would have happened? You would probably have gotten here R to the 5th. Then this would have been what? When you integrate this, it would have been R to the 6 over 6, right? R to the 6 over 6. And then you would do this integral, you would have gotten R cubed, and then you would have gotten R to the 4th over 4. And then when you substitute that, it would have been here 4m R to the 4th, and then that goes over there, 4m R to the 4th, so you have 4 over 6, which is 2/3 mr squared. Okay? Now, if the density had been increasing more rapidly, the moment of inertia of that is 2/3 mr squared, whereas this is 3/5 mr squared. So which one's harder to rotate? The 2/3 is a bigger ratio than 3/5, right? So you can see the pattern here. The quicker the density increases, the harder the material is to rotate. I could also make it R to the -1, R to the -2, R to the -3, right? And then it'll be easier to rotate than the uniform cylinder. Okay? So now I'm going to show you next non-uniform sphere.